cosmic microwave background, CMB, radiation is a faint glow of light that fills the universe and is a remnant of the Big Bang, which occurred approximately 13.8 billion years ago. This radiation provides a critical window into the early moments of the universe's formation and has been a cornerstone in understanding cosmology. Key aspects of the CMB stands for cosmic microwave background. Number 1. Origin. The story of the cosmic microwave background, CMB, begins in the earliest moments of the universe just after the Big Bang, when everything was incredibly hot and dense. During this initial phase, the universe was a seething plasma of particles, including protons, neutrons, electrons, and photons. The intense temperatures meant that particles constantly collided, breaking apart any attempt for them to combine into stable atoms. This created an opaque environment where photons couldn't travel far before scattering off free electrons. As the universe expanded, it also began to cool. Over time, this cooling allowed the dense plasma to transform into a less chaotic state. The energy of the particles decreased, and the collisions became less frequent. By about 380,000 years after the Big Bang, the temperature of the universe had dropped to roughly 3,000 Kelvin. At this temperature, protons and electrons were able to combine for the first time, forming neutral hydrogen atoms in a process known as recombination. The formation of neutral atoms had a profound impact on the universe. With no free electrons to scatter them, photons could now travel freely through space. This event marked the decoupling of light and matter, and the universe became transparent. These photons, which were once trapped in the dense plasma, began to move unimpeded, filling the universe with a faint glow of light. This light is what we now observe as the CMB. The photons from the CMB were initially emitted with very high energy in the visible and ultraviolet spectrum. However, as the universe expanded over billions of years, the wavelength of this radiation stretched due to the redshift effect. Today, these photons are observed as microwave radiation with a temperature of just 2.73 Kelvin, only slightly above absolute zero. The discovery of the CMB was accidental. In 1965, Arno Penzias and Robert Wilson, working on a radio antenna, detected a faint, persistent noise that seemed to come from every direction in the sky. They initially thought it was interference from their equipment or environmental factors, but they soon realized they had stumbled upon a relic of the early universe. This discovery earned them the Nobel Prize in Physics. The significance of the CMB lies in the wealth of information it provides about the early universe. It acts as a snapshot of the cosmos at the time of recombination, preserving the conditions and structures that existed back then. Tiny fluctuations in the temperature of the CMB, observed as anisotropies, correspond to regions of slightly different densities. These density variations served as the seeds for the formation of galaxies and large-scale cosmic structures. Detailed mapping of the CMB began with the COBE satellite in the 1990s, followed by more precise missions like WMAP and Planck. These missions revealed the CMB's fine structure, showing patterns that correspond to the density waves that existed in the early universe. The data from these missions confirmed key aspects of the Big Bang theory and provided critical constraints on cosmological models. The CMB also provides a window into the universe's composition. By analyzing its properties, scientists determined that the universe is made up of about 5% ordinary matter, 27% dark matter, and 68% dark energy. These findings have reshaped our understanding of the cosmos and introduced profound questions about the nature of dark matter and dark energy. Moreover, the CMB is a powerful tool for understanding the geometry of the universe. Measurements of its temperature fluctuations suggest that the universe is flat, meaning its overall curvature is zero. This has implications for the fate of the cosmos and supports the idea of an infinite, ever-expanding universe. One of the most fascinating aspects of the CMB is its connection to cosmic inflation. The patterns observed in the CMB strongly support the theory that the universe underwent a rapid period of exponential expansion in its first fractions of a second. This inflation smoothed out irregularities and explains the large-scale uniformity of the CMB while preserving the small-scale fluctuations we observe today. The study of the CMB continues to evolve. Modern research focuses on its polarization, which can reveal even more about the universe's early moments. In particular, scientists are looking for evidence of primordial gravitational waves, which would provide direct proof of inflation and offer insights into the fundamental physics of the Big Bang. Despite its faintness, the CMB is omnipresent, filling the entire universe. Its uniformity and isotropy are remarkable, but the tiny anisotropies it contains are even more significant. These minute differences in temperature and density laid the groundwork for the vast and complex structures we see in the universe today. The CMB also serves as a time capsule, carrying information about a universe that was vastly different from the one we inhabit. It connects us to a time when matter and light were inseparable, revealing how the cosmos transitioned from a primordial plasma to a structured expanse of galaxies, stars, and planets. Understanding the CMB is not just about looking back in time, it also helps us predict the future. By studying its properties, scientists gain insights into the ultimate fate of the universe, whether it will continue expanding forever, slow down, or collapse back in on itself. The discovery and study of the CMB have also inspired technological advancements. Instruments developed to detect and analyze it have found applications in other fields, showcasing how fundamental research can lead to unexpected innovations. In essence, the CMB is a silent witness to the universe's birth, holding clues to its origins, evolution, and destiny. It bridges the gap between the past and the present, connecting us to the moment of creation. As our tools and theories improve, the CMB will undoubtedly continue to reveal new secrets about the cosmos. Number 2. Characteristics. The cosmic microwave background radiation is remarkable for its uniformity. Its temperature is nearly constant across the sky, measuring approximately 2.73 Kelvin, just above absolute zero. This uniformity reflects the homogeneity of the early universe, where matter and energy were distributed almost evenly throughout space. However, this near-perfect uniformity is not absolute. Tiny fluctuations, known as anisotropies, exist within the CMB, and these minute differences hold critical clues about the universe's early days. These anisotropies are incredibly small, typically varying by only a few millionths of a degree. Despite their subtlety, they represent significant physical processes. These fluctuations correspond to slight variations in density in the primordial plasma of the universe. Regions with slightly higher density had stronger gravitational pull, while regions with lower density had weaker pull. These variations were the seeds for all the large-scale structures we observe today, such as galaxies, clusters of galaxies, and cosmic voids. The origin of these fluctuations lies in quantum mechanics. During the inflationary period of the universe, quantum fluctuations were stretched to macroscopic scales due to the rapid expansion. These fluctuations became imprinted in the density and temperature of the universe, eventually manifesting as the anisotropies we observe in the CMB. These small variations in density provided the framework for the gravitational collapse that would later form stars, galaxies, and other structures. One of the fascinating aspects of the CMB is how these fluctuations are mapped. Satellites like COBE, WMAP, and Planck have created detailed maps of the CMB's temperature variations. These maps reveal a pattern of hot and cold spots, which correspond to regions of slightly higher or lower energy density in the early universe. By analyzing these patterns, scientists can learn about the physical processes that shape the cosmos. The temperature fluctuations in the CMB are not random but exhibit a specific statistical distribution. This distribution reflects the physics of sound waves propagating through the primordial plasma. Before recombination, photons and baryons, protons and neutrons, were tightly coupled and pressure waves traveled through the medium. The peaks and troughs of these waves are imprinted in the CMB as regions of slightly higher and lower temperature. These sound waves, also known as acoustic oscillations, leave distinct signatures in the CMB. For example, the size of the hottest and coldest regions in the CMB corresponds to the sound horizon, the maximum distance sound waves could travel before recombination. Measuring this scale provides valuable information about the size and age of the universe. Another critical feature of the CMB anisotropies is their polarization. When the CMB photons scattered off free electrons during recombination, they became slightly polarized. The pattern of this polarization is directly related to the density and velocity of matter in the early universe. By studying the polarization of the CMB, scientists can gain deeper insights into the processes that occurred during the universe's infancy. The anisotropies in the CMB also provide evidence for the universe's composition. By analyzing the detailed structure of the temperature fluctuations, cosmologists have determined that the universe is composed of approximately 5% ordinary matter, 27% dark matter, and 68% dark energy. These findings are consistent with other observations, such as the large-scale distribution of galaxies and the accelerated expansion of the universe. The CMB's uniformity and anisotropies also offer clues about the universe's overall geometry. Observations of the CMB indicate that the universe is flat, meaning that its spatial curvature is negligible on large scales. This result has profound implications for cosmology, as it suggests that the universe will continue expanding indefinitely. One of the most intriguing questions in cosmology is the nature of the dark components of the universe. While dark matter and dark energy cannot be observed directly, their effects are imprinted in the CMB. The patterns of temperature and polarization fluctuations reveal how these mysterious components influence the evolution of the universe. The anisotropies in the CMB also provide a timeline for cosmic history. By measuring the size and amplitude of the fluctuations, scientists can estimate when key events occurred, such as the epoch of recombination and the subsequent formation of the first stars and galaxies. These observations allow us to reconstruct the universe's evolution with remarkable precision. The study of CMB anisotropies has also shed light on the process of cosmic inflation. The specific pattern of fluctuations observed in the CMB supports the idea that the universe underwent a rapid period of expansion in its first fractions of a second. This inflationary period smoothed out large-scale irregularities while amplifying small-scale quantum fluctuations, creating the conditions necessary for the formation of cosmic structures. Despite its faintness, the CMB continues to play a central role in cosmology. The tiny anisotropies it contains have been studied in ever-increasing detail, revealing a wealth of information about the early universe. Each new observation refines our understanding of the cosmos and poses new questions about its origins and future. Modern instruments have reached incredible levels of sensitivity, allowing scientists to detect even subtler features in the CMB. For example, researchers are now studying the B-mode polarization of the CMB, which is thought to be a signature of primordial gravitational waves. Detecting these waves would provide direct evidence for cosmic inflation and offer a glimpse into the universe's earliest moments. The anisotropies in the CMB are also a reminder of the interconnectedness of the cosmos. The tiny differences in temperature and density observed today are directly linked to processes that occurred billions of years ago. These fluctuations are a testament to the complex interplay of physics, from quantum mechanics to general relativity, that governs the universe. The near uniformity of the CMB serves as a cosmic baseline, against which the tiny anisotropies stand out. This combination of simplicity and complexity makes the CMB a unique and invaluable tool for understanding the universe. It is both a relic of the past and a guide to the future, connecting us to the origins of space and time. As we continue to study the CMB, we uncover new layers of complexity in its anisotropies. Each new discovery brings us closer to answering some of the most profound questions about the universe. How did it begin? What is it made of? And what is its ultimate fate? The CMB remains a cornerstone of cosmological research, a silent witness to the birth of the cosmos and a key to unlocking its mysteries. Number 3. Detection. The discovery of the cosmic microwave background, CMB, radiation was a turning point in cosmology. In 1965, Arno Penzias and Robert Wilson, working at the Bell Telephone Laboratories in Holmdel, New Jersey, were using a horn antenna to study radio signals. They were attempting to refine the technology for satellite communications but encountered an unexpected problem. A persistent, low-level noise interfered with their observations, and it seemed to come from every direction in the sky. Initially, Penzias and Wilson believed the noise was due to a flaw in their equipment or external interference. They meticulously checked their apparatus, even cleaning out bird droppings from the antenna, but the noise persisted. The signal had no discernible source and appeared isotropic, meaning it was evenly distributed across the sky. After ruling out all possible causes, they realized they had stumbled upon something extraordinary. At the same time, a team of physicists led by Robert Dicke at Princeton University was working on a theoretical prediction related to the Big Bang. Based on earlier work by George Gamow, Ralph Alpher, and Robert Herman, Dicke's group predicted that the early universe would have left behind a faint glow of radiation, now cooled to microwave wavelengths. When Penzias and Wilson communicated their findings to the Princeton team, it became clear that the noise they detected was the relic radiation from the Big Bang. This discovery provided compelling evidence for the Big Bang theory, which posits that the universe began as a hot, dense state and has been expanding ever since. The CMB was the remnant heat from that initial explosion, now stretched to microwaves by the universe's expansion. For their groundbreaking discovery, Penzias and Wilson were awarded the Nobel Prize in Physics in 1978. Following its discovery, efforts to study the CMB in greater detail intensified. Ground-based and balloon-borne experiments provided early insights, but these methods were limited by atmospheric interference. To overcome this, scientists turned to space-based observatories. The first major breakthrough came with the launch of the Cosmic Background Explorer (COBE) satellite in 1989. COBE was designed to measure the CMB with unprecedented accuracy. It confirmed that the radiation was a nearly perfect blackbody spectrum, as predicted by theory, and detected small anisotropies in its temperature. These temperature fluctuations were critical for understanding the density variations in the early universe. COBE's results earned its lead scientists John Mather and George Smoot the Nobel Prize in 2006. Building on COBE's success, the Wilkinson Microwave Anisotropy Probe, WMAP, was launched in 2001. WMAP provided much higher resolution data, mapping the temperature fluctuations of the CMB with incredible precision. Its observations refined estimates of key cosmological parameters, such as the age of the universe, the composition of its matter and energy, and the rate of its expansion. MAP's data confirmed that the universe is approximately 13.8 billion years old and flat on large scales. The most detailed study of the CMB to date came with the European Space Agency's Planck satellite, launched in 2009. Planck improved on MAP's resolution and sensitivity, allowing for a more detailed analysis of the CMB's anisotropies. It also measured the polarization of the CMB, which provided additional insights into the universe's early conditions and the physics of cosmic inflation. Planck's results were groundbreaking. They revealed the fine structure of the CMB with unprecedented clarity, enabling scientists to study the tiny temperature variations in greater detail. These observations confirmed and refined the standard model of cosmology, known as the lambda cold dark matter model, lambda CDM. This model describes the universe as being composed of 68% dark energy, 27% dark matter, and 5% ordinary matter. The detection and mapping of the CMB have also shed light on the universe's large-scale geometry. The observations confirm that the universe is flat, meaning it has no overall curvature, consistent with predictions from inflationary theory. This flatness implies that the total energy density of the universe is equal to the critical density. Another critical aspect of CMB detection is its polarization. When CMB photons scattered off free electrons during recombination, they became slightly polarized. This polarization pattern contains information about the density and velocity of matter in the early universe. Planck and other experiments have used polarization data to study the physics of recombination and probe the presence of primordial gravitational waves. The detection of the CMB has also inspired technological advancements. The instruments developed for these missions have applications in fields such as telecommunications, imaging, and data analysis. The success of CMB research highlights the interplay between fundamental science and technological innovation. Ground-based observatories continue to complement space-based missions. Projects like the Atacama Cosmology Telescope and the South Pole Telescope focus on specific features of the CMB, such as its polarization and small-scale anisotropies. These efforts aim to refine our understanding of cosmic inflation and the properties of dark matter and dark energy. The detection of the CMB is a testament to the power of collaboration in science. From the serendipitous discovery by Penzias and Wilson to the sophisticated analyses by modern satellites, the study of the CMB has involved contributions from physicists, engineers, and astronomers worldwide. Each new discovery builds on the work of previous generations. Despite its faintness, the CMB has proven to be one of the most valuable tools for understanding the universe. Its detection confirmed the Big Bang theory and provided a framework for modern cosmology. The ongoing analysis of the CMB continues to refine our understanding of the universe's origins, composition, and evolution. The fine structure of the CMB is a cosmic fingerprint, carrying the imprint of the universe's earliest moments. By studying it, scientists can trace the history of the cosmos from the first fractions of a second after the Big Bang to its current state. This makes the CMB a cornerstone of cosmological research. The detection of the CMB also serves as a reminder of the interconnectedness of scientific discovery. Theoretical predictions, observational breakthroughs, and technological advancements have all played a role in uncovering this relic of the early universe. Together, they provide a clearer picture of the cosmos and its origins. The story of the CMB is far from over. As new instruments and techniques are developed, the study of this ancient radiation will continue to reveal new insights into the nature of the universe. Each discovery brings us closer to answering the profound questions about our place in the cosmos. Number 4. Insights provided. The cosmic microwave background, CMB, provides a window into the universe's early moments, offering unparalleled insights into its age. By measuring the small fluctuations in the CMB's temperature and polarization, scientists have determined that the universe is approximately 13.8 billion years old. These precise measurements rely on the detailed mapping of the CMB, which allows researchers to reconstruct the timeline of cosmic events, from the Big Bang to the present day. This age estimate stems from the ability to measure the universe's expansion rate, known as the Hubble constant, and its overall density. The CMB serves as a snapshot of the universe when it was just 380,000 years old, providing a critical anchor point for understanding its subsequent evolution. By analyzing the size of the temperature fluctuations in the CMB, scientists can infer the rate of expansion and calculate the universe's age with remarkable precision. The CMB also sheds light on the composition of the universe. It confirms that ordinary matter, atoms and molecules, makes up only about 5% of the universe's total energy density. The remaining 95% consists of dark matter and dark energy, which are invisible and interact with ordinary matter primarily through gravity. Dark matter, comprising about 27%, provides the scaffolding for galaxy formation, while dark energy, which constitutes 68%, drives the accelerated expansion of the universe. These proportions were determined by studying the detailed structure of the CMB's anisotropies. The specific patterns of temperature fluctuations correspond to variations in the density of matter and energy in the early universe. By analyzing these patterns, cosmologists have been able to confirm the dominance of dark components and refine their understanding of how they influence cosmic evolution. Another key insight from the CMB is the geometry of the universe. Observations reveal that the universe is flat on large scales, meaning its spatial curvature is negligible. This conclusion is drawn from the size and distribution of the temperature fluctuations in the CMB, which match the predictions of a flat universe in the Standard Model of cosmology. A flat geometry implies that the total energy density of the universe is precisely balanced with its critical density. The flatness of the universe has profound implications for cosmology. It supports the idea that the universe underwent a period of rapid inflation in its earliest moments. Inflation smoothed out any initial irregularities in the universe's shape and stretched it to such an extent that its curvature is now indistinguishable from flatness on observable scales. This flat geometry is consistent with the predictions of inflationary theory, strengthening its status as a cornerstone of modern cosmology. The CMB also provides evidence for inflation through the patterns in its temperature and polarization anisotropies. Inflation predicts that quantum fluctuations in the early universe were stretched to macroscopic scales, creating the seeds for the density variations observed in the CMB. These fluctuations are imprinted as specific statistical patterns in the CMB, which match the predictions of inflationary models with remarkable accuracy. One of the most compelling pieces of evidence for inflation is the uniformity of the CMB. Despite originating from regions of the universe that were not in causal contact at the time of recombination, the CMB's temperature is nearly identical everywhere. Inflation explains this uniformity by proposing that all regions of the observable universe were once in close contact before being rapidly stretched apart. The polarization of the CMB provides additional insights into inflation. Certain polarization patterns, known as B-modes, are thought to be signatures of primordial gravitational waves generated during inflation. While these signals are faint and challenging to detect, their presence would offer direct evidence for the inflationary process and provide clues about the physics of the universe's earliest moments. The CMB's detailed structure also helps refine our understanding of cosmic history. By studying the size and distribution of its temperature fluctuations, scientists can determine when key events occurred, such as the formation of the first atoms during recombination and the emergence of the first stars and galaxies. These observations create a timeline of the universe's evolution, linking the CMB to later cosmic phenomena. Another insight gained from the CMB is the role of dark matter in shaping the universe. The anisotropies in the CMB reveal how dark matter influenced the growth of density fluctuations. Unlike ordinary matter, which interacts with radiation and was smoothed out in the early universe, dark matter clumped together, providing the gravitational framework for galaxy formation. The CMB also offers clues about the mysterious nature of dark energy. While dark energy cannot be observed directly, its effects are imprinted in the CMB through its influence on the universe's expansion rate. By comparing the CMB's properties to the distribution of galaxies in the present-day universe, cosmologists have been able to constrain the properties of dark energy and understand its role in cosmic evolution. The ability of the CMB to probe such fundamental aspects of the universe stems from its origin as a relic of the Big Bang. As the oldest light we can observe, it serves as a time capsule, preserving information about the universe's initial conditions. Each fluctuation in the CMB's temperature corresponds to a density variation in the primordial plasma, offering a direct link to the earliest moments of cosmic history. By studying the CMB, scientists have also been able to test and refine the standard model of cosmology, known as the lambda cold dark matter, lambda CDM, model. The CMB provides strong support for this model, confirming its predictions about the universe's composition, geometry, and evolution. At the same time, it raises new questions about the nature of dark matter, dark energy, and the physics of inflation. The insights provided by the CMB have been instrumental in transforming cosmology into a precision science. Measurements of the CMB have reduced uncertainties in key cosmological parameters, enabling researchers to make more accurate predictions about the universe's future and its ultimate fate. These advancements highlight the power of the CMB as a tool for understanding the cosmos. Despite its faintness, the CMB contains a wealth of information about the universe's origins and structure. Its discovery and subsequent study have revolutionized our understanding of the cosmos, offering a unified framework for explaining its past, present, and future. Each new observation builds on this foundation, revealing new layers of complexity in the universe's story. The CMB's insights into the age, composition, geometry, and inflationary history of the universe underscore its significance as a cornerstone of modern cosmology. As technology and techniques improve, the study of the CMB will continue to refine our understanding of the cosmos, addressing some of the most profound questions about its nature and origin. Number 5. Ongoing research. Ongoing research into the cosmic microwave background, CMB, focuses on uncovering the secrets of the universe's earliest moments and its mysterious components. One key area is the study of the CMB's polarization, which carries imprints of the physical processes that occurred during the inflationary period. By analyzing the polarization patterns, scientists hope to detect signals of primordial gravitational waves, which would provide direct evidence of cosmic inflation and insights into the high-energy physics of the early universe. Polarization in the CMB arises when the light from the early universe scatters off free electrons in the primordial plasma. This scattering creates distinct polarization patterns, known as E modes and B modes. E modes are relatively easier to detect and have already been mapped in great detail, revealing valuable information about the density and velocity of matter in the early universe. B modes, however, are much fainter and more challenging to observe but are considered crucial for studying inflation. Detecting B-mode polarization would be a groundbreaking achievement, as it could confirm the existence of gravitational waves generated during inflation. These waves would have stretched and squeezed space-time, leaving a faint but unique imprint in the polarization of the CMB. Advanced telescopes and detectors are being developed to search for this signal, which would provide a direct link to the physics of the universe's first fractions of a second. The study of the CMB's polarization also offers a way to test competing models of inflation. Different inflationary theories predict varying patterns of gravitational waves and polarization. By comparing observations with theoretical predictions, scientists can narrow down the possible scenarios and gain a better understanding of the mechanisms that drove the rapid expansion of the universe. Ongoing research into the CMB also aims to shed light on the nature of dark matter. While dark matter does not emit or absorb light, its gravitational effects influence the distribution of matter and energy in the early universe. These effects are imprinted in the CMB's temperature and polarization anisotropies. By studying these patterns, researchers can infer properties of dark matter, such as its mass and interactions, and test theories about its composition. Dark energy, the mysterious force driving the accelerated expansion of the universe, is another focus of CMB research. Observations of the CMB provide a critical benchmark for understanding the universe's expansion history. By combining CMB data with measurements of the large-scale structure of the universe and supernova observations, scientists can refine models of dark energy and explore its role in cosmic evolution. Advanced CMB studies also involve improving the precision of cosmological parameters. Parameters like the Hubble constant, the density of dark matter, and the scale of inflation are derived from the detailed analysis of the CMB's anisotropies. Each new generation of instruments provides more accurate measurements, helping to resolve discrepancies and refine the standard model of cosmology. Ground-based observatories such as the Atacama Cosmology Telescope and the South Pole Telescope play a vital role in ongoing CMB research. These facilities are designed to observe the CMB with high sensitivity and resolution, focusing on small-scale anisotropies and polarization signals. Their data complement the results from space-based missions and provide additional insights into the fine structure of the CMB. Future space missions such as the proposed CMB-S4 project and next-generation satellite observatories aim to push the boundaries of CMB research. These missions will combine unprecedented sensitivity with advanced technology to explore the faintest signals in the CMB. Their goals include detecting B-mode polarization, mapping the CMB's polarization across the entire sky, and probing the physics of the early universe with unparalleled precision. The study of the CMB's polarization also extends to understanding reionization, a key phase in cosmic history. After the first stars and galaxies formed, their radiation reionized the neutral hydrogen in the universe. This process left an imprint in the CMB's polarization, which researchers analyzed to reconstruct the timeline of reionization and study the properties of the first luminous objects. Ongoing CMB research also explores the potential connections between the CMB and fundamental physics. For example, certain anomalies in the CMB's temperature distribution, such as the so-called cold spot, may hint at new physics beyond the standard model. These anomalies are subjects of intense investigation, as they could reveal unknown aspects of the universe's structure or early conditions. Scientists are also using the CMB to test theories about the nature of space and time. The uniformity and isotropy of the CMB provide a laboratory for studying the fundamental principles of relativity and quantum mechanics. Any deviations from expected patterns could point to new physics or insights into the unification of fundamental forces. The search for primordial non-Gaussianities in the CMB is another area of ongoing research. Non-Gaussianities are deviations from the simple statistical patterns predicted by standard inflationary models. Detecting these deviations would provide clues about the interactions of particles in the early universe and help distinguish between different inflationary scenarios. Ongoing CMB research also involves studying the integrated Sachs-Wolf effect, a phenomenon where photons from the CMB gain energy as they pass through evolving gravitational potentials. This effect provides a way to study the dynamics of dark energy and its impact on the universe's large-scale structure. Combining CMB data with galaxy surveys enhances the study of this effect. Cross-correlation studies between the CMB and other cosmic signals are becoming increasingly important. By comparing CMB observations with data from galaxy surveys, gravitational lensing maps, and other astrophysical probes, researchers can gain a more comprehensive understanding of the universe's composition and evolution. These multi-messenger approaches are crucial for addressing complex questions in cosmology. One of the challenges in ongoing CMB research is minimizing contamination from foreground signals, such as emissions from our galaxy and extragalactic sources. Advanced data processing techniques and improved instrumentation are being developed to separate the CMB signal from these foregrounds, ensuring the accuracy of observations. The study of the CMB also has implications for understanding the future of the universe. By analyzing the expansion history and energy components revealed by the CMB, scientists can make predictions about the ultimate fate of the cosmos. Whether the universe will continue expanding indefinitely, collapse in a big crunch, or experience a new phase of evolution remains an open question. Despite the challenges, the CMB remains one of the most powerful tools for probing the universe's origins and structure. Each new observation and discovery adds to the growing body of knowledge, refining our understanding of the cosmos and raising new questions. The interplay between theory, observation, and technology drives progress in this dynamic field. Ongoing CMB research represents a collaboration of scientists worldwide, drawing on expertise in physics, astronomy, engineering, and data analysis. This global effort reflects the universality of the questions being addressed and the shared goal of uncovering the fundamental nature of the universe. As technology advances and new missions are launched, the CMB will continue to illuminate the mysteries of the cosmos. Significance: the CMB is often described as a snapshot of the infant universe. By studying it, astronomers can trace the universe's evolution from a hot, dense state to the vast, structured cosmos we observe today. It is a critical piece of evidence for the Big Bang theory and remains a focal point for modern astrophysics and cosmology.